Ok. Vou fazer a apresentação em inglês, certo? Que o seminário vai ser em inglês. So welcome to the afternoon session today. We had today one seminar in the morning, international seminar in the morning, and the second one is now with Professor Diego Rubiera. About Diego Rubiera is already a friend of us in our department. He has already been visiting here. So we are very pleased to have him again in our webinar session. Diego has take his master studies in Madrid, his PhD in Oviedo in Spain, and then he moved to different countries for different postdocs. He was first in Paris, and then in João Pessoa, second postdoc. That's where we made the link. And then he moved to Shanghai and then Lisbon. So now he is a junior researcher at the Complutense de Madrid University, and he researched mainly in alternative theories of gravities. His focus in the last work that seems to be in compact objects, and he will talk about singularities in black holes. That is a very, very interesting and hot topic now that we have this confirmation of object that seems to be black holes coming from the gravitational waves measurements recently available to everybody. Okay, so please, Diego, whenever you want.
Ok, obrigado, Vitor Afonso, muito obrigado pelo convite e pela apresentação. Bom, eu falo mais ou menos português, mas para fazer uma palestra científica eu tenho muita mais confidência no meu inglês. É por isso que vou falar em inglês. Vou falar devagar em inglês para que todos vocês podem perceber o que eu vou falar. So as far as Vitor Afonso was saying in the introduction, so I have chosen this topic of singularities. So I think that the title is quite appealing, or at least for me. So because this is a kind of problem that has been within the heart of general relativity for already more than 50 years, this issue with singularities. So there are singularities in the early universe in cosmology and also in black holes, which is the topic I am going to talk about today. So this is mostly a theoretical topic, but it contains some, in my view, this is where the heart of the theoretical problem of general relativity is. This is the place where we have to look in order to find some hints of physics that could be beyond general relativity, which is my main topic of interest, and actually it's a topic with a massive interest in the community nowadays, because thanks to the new field of multi-messenger general astronomy, gravitational waves, so we have new windows of information to look at the universe, so we can start trying our most wild ideas about the behavior of gravity on the most extreme conditions. So singularities become, in some sense, some guidelines of how to modify the theory of general relativity in order to look for new physics, and from there to make contact with experiments. This is something that I am very interested in, making this link between modifications of general relativity motivated by theoretical considerations and how these back react upon the predictions for the physics of compact objects, and that we can measure according to many different experiments nowadays. So I'm not going to talk about astrophysics today. I'm going to talk about a purely theoretical problem, which is the one of singularities. And my starting point is general relativity and black holes. So general relativity is an extremely successful theory of gravitational interaction. So it explains, I should put underline to this word, explains everything that we have measured about the universe. This is not entirely true, because in order for this to happen, we have to add into the model some new matter fields that are not in the original description of the theory, and about which we have no evidence, no direct observational evidence nowadays. Anyway, this is a different topic. So we are going, for the sake of this talk, to assume that general relativity holds, and because it holds, its predictions regarding the properties of black holes have been utterly made met by the observations. So we already have, before the birth of multi-messenger astronomy, quite a lot of evidence about the real, that black holes are real objects in the universe. So basically, this comes from the accretion disk around these objects and using different techniques. So we have a good reasons to suspect that black holes were real, but with the discovery of gravitational waves out of black hole mergers, and moreover, with the imaging of the geodesic motion, which is also known as the shadow of the supermassive central object within an 87 galaxy. So this is out of controversy already. So black holes exist in the universe. They have some properties that are very well described by Einstein general relativity. Einstein general relativity and its field equations tell us that the most general axisymmetric solution, which means the most general solution rotating around some x-axis, is the Kerr-Newman solution. The beauty of this solution, not mathematical beauty, because the expression of its line element is quite complicated. So its beauty is rooted on the fact that it is described by 3 and only 3 parameters. This is very weird because for every physical system that you can thought about in nature, there is no way that you can describe with 3 parameters, and actually you usually need a huge number of parameters. But in the case of black holes, we only need 3, and this is not kind of oversimplification of the solution. It's actually 3, not 2 or 4. It's exactly 3 parameters. And these 3 parameters are the mass, the charge, and the angular momentum. Nonetheless, from the point of view of astrophysical considerations, charge is usually neglected because basically the mass of a black hole is extremely huge, and it dominates completely the behavior over the charge, and the same happens with rotation. So usually you can neglect charge, keep with mass and angular momentum. This is the Kerr solution, and then you can start doing your physics. This physics that we do and we can observe is actually concerned only outside the event horizon. I mean, because no information can come out from inside the black hole, we can only obtain information about this solution from outside. Outside meaning outside the event horizon. Anyway, since the Kerr-Newman solution, general relativity, seems to describe so well everything that we observe about these objects in the universe, maybe we should also start taking seriously the predictions of general relativity for the physics inside black holes, inside the event horizon. But as soon as you start doing this, and this is something that you can do in a graduate course very easily, because it appears in every textbook of general relativity, you find that as soon as you enter into the black hole, there is something weird with the structure of these objects. You can see this very nicely with the Schwarzschild solution, which I have writing here. And there are, in this line element, 2 potential problems with this line element given by the divergences of these metric components at some point or another. So there are two places where any of these components can diverge. The first one is when the radius, or the value of the radial coordinate, equals 2 times the mass. Because in this case, this component goes to 0 and this component goes to infinity. Anyway, as any graduate student knows, this problem, this point is not a problem at all, because it can be, these divergences can be removed out using a change of coordinates. There are many changes of coordinates by which you can transform this line element into something where there are no divergences of the components of the metric. For instance, the Eddington-Fickstein one probably is the the most well-known change of coordinates. And this is just has to do with the freedom that we have in general relativity of the parametrization of the physics using different system of coordinates. Actually, this is a manifestation of deep principles of physics by which the physics of any object shouldn't depend on which system of coordinates I'm using. The problem lies when the value of the radial coordinate goes to 0. Because in this case, there is no change of coordinates by which the divergences of this component of the line element can be removed. And you can check this by computing something that does not depend on the system of coordinates you are using. For instance, using curvature scalars. Here I have computed the Kretschmann, which is just the Riemann square, and you find the result for the Schwarzschild solution. And because it goes with the inverse of r to the 6, you find that when r goes to 0, this scalar diverges. So this singularity, let's call it this way, that happens in the Schwarzschild solution cannot be removed by a change of coordinates. It's an essential singularity of your spacetime. So I have been using here a Schwarzschild solution, which is described only by mass, but if I use the Reisner-Nostrom solution, which is described by mass and charge, I will find the same result, that there is a point-like curvature divergence at the center of the solution. And if you use the Kerr-Newman solution, there is also a singularity, a curvature divergence at the center of the solution, but in this case, it has a ring-like shape. So this is why I'm using the word curvature divergence and the word singularity to describe this problem at the center of the solution. Okay. So having understood this, so things are not that weird. So because if we want to detect the presence of a singularity in general relativity, we just need to compute the behavior of curvature scalars, and if there is any curvature scalar that goes to infinity, then we have a singularity. So if you want to have a space-time without singularities, that's it. A non-singular space-time, we just need to make sure that in your space-time, all curvature invariants are finite. Are you listening to me? Is there any problem with the audio or something? It's okay?
Okay, Diego.
Okay.
It's okay.
Okay, thank you very much. Okay, so this is the point where we were. So if we want to have a non-singular spacetime, just make all curvature invariants finite. Is it?
Diego, sorry to interrupt. Em nossos seminários, é normal, a gente permite que as pessoas façam perguntas de vez em quando, se elas querem. Te incomoda?
Ótimo. Não, é perfeito para mim.
Tudo bem.
Podem perguntar quando quiserem.
Ok, obrigado.
Ótimo. Okay. So the question is this reasoning true? There is a problem with this kind of argument. These divergences that we are computing with the blow-up of curvature scalars, this is something fundamentally different from any other kind of singularities we are used to. We are used to singularities that happens on fields that live on a fixed space-time background. For instance, the divergence of Coulomb in classical electrodynamics. But in the case of general relativity, if the space-time, the line element breaks down at some point, how we can even speak of a singularity as something that occurs at some location when the space-time manifold is broken at that location? This is not a kind of linguistic problem. It is that actually it is quite known that the general characterization of singularities by computing the blow-up of curvature scalars is unsatisfactory due to different reasons. Because, first of all, because there are examples of perfectly regular spacetimes that have some problems with the curvature scalars. And the other way around, the amount of yield behavior of curvature scalars is exceedingly large. So you should compute a lot of different curvature scalars trying to characterize a singularity, but you could never ever be sure that there is not a curvature scalar that diverges, because there is a lot from a mathematical point of view. So instead of using curvature, which is very ingrained upon our conceptual understanding of classical gravitation, we tend to believe the curvature is something physical in the sense that it's something directly observable. But this is not true. This is not directly observable. Only its effects upon physical observers is directly observable. So I would like to have a more sensible and direct physical way to look to see whether there is any kind of pathology, any kind of problem with our solutions. This is exactly what the well-known theories on singularities do. They capture the essence of this problem, but by, instead of using the behavioral curvature, using the trajectories of particles, in particular the free-falling trajectory of particles, which are known as geodesics. And in these theorems, they prove, in one of their formulations of the theorems, because there are several, that it's these three conditions, which are the null congruence condition, which is related to the null energy condition, general relativity. If the second condition is the development of an even horizon, and the third condition, which is the existence of a well-defined hypersurface upon which you can define a well-posed initial data problem, which is called, which is known as a Cauchy hypersurface. If these three conditions hold, then your space-time contains at least one incomplete geodesic. And this is a very important result because these three conditions are very general. This is just, the first condition is just a very reasonable condition upon your matter fields that satisfy standard energy conditions. The third condition is just a well-posed initial data problem. And the second condition is that we have a black hole, which is the kind of objects we're interested in. So these theorems tell us that you have an incomplete geodesic. And why is this so problematic? The problem is that time-like geodesics are associated to the free fall of physical observers, while null geodesics are associated to the propagation of photons, that's it, the propagation of light and the transmission of information. But such geodesics should be complete always, because if this were not the case, as I'm representing here in this figure, then you will have a space-time where the trajectory of your particle or the trajectory of your photon disappears from the space-time at some finite time in the future or in the past. So in these space-times where you have incomplete geodesics, you have observers that suddenly disappear from the manifold or suddenly emerge out of nowhere. This situation should be surely forbidden because otherwise we will not have predictability and determinism conserved in your physical theories. This is something that we should forbid. And in this sense, the fact that the observers might experience intense tidal forces, which is related to the behavior of curvature scalars, is completely secondary as long as these observers exist. So the first thing that you need to go for is to guarantee that your physical observers and your trajectories of light exist always. And once you have guaranteed that these trajectories always exist, then you can be concerned yourself with what will happen to a physical observer that overcomes a region where the curvature is arbitrarily large. Or in other words, this is a sentence I have borrowed from Professor Alfonso, which is that the existence of observers, which is what geodesic completeness tell us, is more important than the suffering, which is what curvature divergences tell us. Therefore, the summary of this discussion is that in a singular space-time, like in the Schwarzschild solution, there will be geodesic curves that cannot be extended to arbitrarily large values of the affine parameter. That's it. They will finish or their trajectories at some time in the future, or they will come out of nowhere at some time in the past. Therefore, if you want to have a non-singular space-time, the first thing that you need to do is to guarantee that all your geodesics in your space-time are complete. And this is going to be absolutely independent of what curvature scalars do or do not do. Then, when you open any textbook upon this subject, or even papers in the literature, even today, if you check archive, almost every day there is a paper about this thing where people study the behavior of curvature scalars. So why do they do this if we already know that the key concept in singularities is the geodesic completeness? The reason is very simple and very naive at the same time. It's because in most cases of interest, those spacetimes where curvature divergences are present, they turn out also to be geodesically incomplete. And because it's much easier to characterize the behavior of curvatures than the behavior of geodesics, actually you can do this with even with the exact program of Mathematica that last year when I was in Campina Grande, Professor Gonzalo Olmo was giving a full short course on how to use this program. But this is just a matter of convenience when you study your favorite spacetime, but the key concept here is the one of geodesic completeness. The one of curvature divergences could be simpler to characterize, but in order to guarantee that your spacetime is well behaved, the first thing that you need to do is to study geodesic completeness. And from that point of view, it is very easy to check, this is an exercise for a graduate student, that both Schwarzschild and Reisner-Nostrom solutions are singular solutions. So the general conclusion of this part of my talk is that the theorems on singularities determine that the existence of incomplete geodesics that we can see as some kind of holes in the fabric of space-time, and using the word holes because it looks like some place where geodesics fall without coming back, or they emerge out of there. And these theories on singularities tell us that singularities do occur in general relativity. They occur under very general assumptions. So if general relativity is the right theory of space-time, so we have a problem with the understanding of this thing. So, any sensible ideas to deal with this problem? Of course, there are many in the literature. You can pick your favorite approach to this problem. I am going to pick something which is a bit unusual, which is an idea borrowed from condensed matter systems. So keep with me for 1 minute and you are going to see where I'm heading to using this analogy. So what is a crystalline structure in solid-state physics? So it's nothing strange, it's just a regular pattern of atoms, this one. So this pattern of atoms describe the microstructure of your material. And then there is the possibility of making a continual limit of this structure. And then you find the usual laws that you find in any textbook on solid-state physics. The point is that any real crystalline structure will have defects on the microstructure. This is unavoidable. These defects are always there. And defects are of different kinds. I'm depicting here some of them. So, for instance, here there is an atom which is missing. Here there is an atom which is placed in a place where it shouldn't be. This will be point light defects, but there are also line light defects, like this line of atoms that has no continuity here, or is broken. So, in any crystal, the density of defects of point light, line light, and also two-dimensional defects is non-zero. And these defects have dynamics. They are not static there, but they actually move like they were real particles of real extended structures. What is the point of bringing this thing upon our attention? The point is that when you make the continual limit of this microstructure to the full system, you find that in this continual limit, you find the usual concepts that we have about the intuitive idea of metric and the intuitive idea of connection. The intuitive idea of metric is just counting atoms, jumping from one to the other, while the idea of connection, heuristically, is just following any of the lines connecting the different atoms. Of course, this can be mathematized into a much more rigorous and systematic way. But this is for our interest. For the interest of this talk, we just can keep with this idea. Anyway, if you are more interested in this, just open your favorite solid-state physics book, and you will always see some kind of a small section talking a bit about this. What is the point of this thing? That when you do the continual limit of a crystalline system with defects, the geometry that comes out of this continual limit depends on the type of defects that you have in your material. If you only have point-like defects, it can be mathematically proven that these point-like defects induce the existence of non-metricity. And non-metricity is just the failure of the connection to be metric. The failure, the fact that the covariant derivative of the spacetime metric is different from zero. In the same way, if you make the continual limit of a crystalline structure that contains a light defect like this one, then you will find that the geometrical structure that you need in order to describe this procedure is torsion. And then what happens with the Riemannian geometry that we have in general relativity, where the metric and the connection are compatible? This could correspond to the idealized crystal where there are no defects at all. But because defects are there, they are always present in any kind of material, then in general, you need independent metric and connection in order to account for the existence of these defects in the microstructure of the material in order to make the right continual limit. So, lesson from this part is that the usual Riemannian geometry that we are used to in general relativity is not the only consistent geometry to describe physical phenomena. So, the question that remains here is precisely to determine which is the geometry which is more suitable in order to describe any phenomena of interest. In our case, because we do gravitational physics, we are interested on determining which is the physical geometry to deal with gravitational phenomena. Because black holes, any other compact objects, cosmology, and so on, are purely gravitational phenomena. So the question of whether and which geometry should we use is non-trivial at all. So we have just seen that in order to deal with continuous systems that have defects on the microstructure, we need to upgrade Riemannian geometry to other geometries, including having independent metric and connection. So the question, could be this lack of versatility of Riemannian geometry that we find in crystalline structure with defects to account for the macroscopic limit of these structures, could this be the reason for the existence of a space-time singularity? Or, in other words, the reason for our inability to deal with space-time singularities? So what will happen if we, instead of formulating gravitation in Riemannian spaces, the one we are used to in general relativity, if we formulated it in non-Riemannian spaces? This is something that should not be ruled out a priori. It is nature, the one who should tell us which one is the right geometry of the space-time. This is a question to be determined upon experimentation, not by tradition or convention, which is the standard way that you find in textbooks in order to deal with this problem. Okay, so this is the first part of my talk. Unless you have any questions about this part, I'm going to make use of these ideas in order to build my own contribution to this topic. Okay, so up to now, I'm just making an account of what is more or less known in the literature, at least from my perspective. And then I'm going to enter into my own approach to this problem. So in this approach to this problem, as I have justified the need to have independent metric and connection, this is usually called or known as metric-affine gravities. The name comes simply for the fact that we have metric and affine connection which are independent. Now, there are many different metric-affine theories in the literature. For the sake of this talk, I'm just using a family has a series of nice properties, as I'm going to mention right now, which are called Ricci-based gravities, or for the sake of this, all RBGs to shorten the notation. So this is something very simple. So it's the same thing that you have in general relativity, excepting that instead of having here in the gravitational Lagrangian the curvature scalar, you have some function that depends on the metric and on the Ricci tensor. It's the Ricci tensor because it is the object that depends on the connection, and because the connection is independent from the metric. So, for instance, if this Lagrangian, instead of the functional form is R equal to G mu nu contracted with R mu nu, this is the curvature scalar, and this is general relativity. But we don't need to constrain ourselves to this scenario. We can go beyond it. So as I'm saying, we are making a fine formalism. Metric and connection are independent objects. So in order to obtain field equations from here, you just need to make independent variations of this action with respect to the metric and connection. But before going there, I'm making some caveats here, which are some oversimplifications in this action. First of all, I'm not introducing torsion because I'm going to deal only with bosons. So actually, Professor Alfonso has worked with these metric affine theories with torsion. So if you are interested in this thing, you can ask directly to him. The second thing is that here in the Ricci tensor is only the symmetric part. In general, even if torsion is 0, the Ricci tensor has an antisymmetric part. I'm removing it from here because in this way I safeguard the theory from Gauss line instabilities, from the propagation of negative energy density modes, which is always the mark of an unstable theory of gravity. And then last point is that this Lagrangian density needs to be a scalar in order to define in order to have a well-defined gravitational action. And you can actually prove that for this object to be a scalar, it must be expressed as powers of traces of this object. So for instance, the simplest object will be with mu and beta are the same thing, and then you have the curvature scalar. But you cannot, then you have general relativity, but you don't need to limit yourself to general relativity. F of R, R mu nu, or infinite spiral gravity theories are examples of this thing. Now, these theories have large advantages, which is that you can always express its field equations upon the Einstein-Ferencz representation. And this is useful because when you have these equations, it looks almost the same as general relativity. I have the Einstein tensor on the left, but instead of the Einstein tensor of some of the spacetime metric G is of some metric Q. Where is this Q? This Q is just a new metric that I introduced by hand here in my theory. Actually, this is not true. You can derive it from the theory, but anyway, let us assume that we introduce it by hand. And it's just the metric the connection, the independent connection is compatible with. So this is like the standard metric connection compatibility equation of general relativity, but acting upon some new effective metric G mu nu. And this effective metric G mu nu is related to the spacetime metric G mu nu via this equation, where this matrix that appears here depends on the theory of gravity you are chosen, but can be always written on cell, I mean, upon the solutions, as functions of the energy momentum tensor. And this means that everything you have here on the right-hand side can be always expressed as function of the energy momentum tensor. So this is just general relativity. It's general relativity for some new metric Q with some new couplings on the matter fields on the right. So it looks like general relativity with a no minimal matter gravity coupling. So no problem. We know how to solve these equations. It's exactly the same that you do in general relativity. And another large advantage of this theory is that they only propagate, these equations are Gauss-free, they are second order, and they only propagate the two polarizations of gravitational field traveling at the speed of light. That's it. They do not have other degrees of freedom, other propagated degrees of freedom rather than gravitational waves. And because they travel at the speed of light, they are compatible with all gravitational wave observations so far. Okay, so far so good. We have a theory of gravity which is consistent. Actually, you can check that if you are in general relativity, if you put here in this gravitational Lagrangian the curvature scalar of general relativity, then these equations give you the Einstein equation of general relativity. Okay. So it means that general relativity can be formulated consistently as a metric affine theory. It gives you exactly the same dynamics and exactly the same predictions. But if this gravitational Lagrangian is something that goes beyond the Einstein-Hilbert Lagrangian of general relativity, then the predictions of the theory are different. Okay, so in order to study black holes, starting with the simplest case, which is the one of spherical symmetric spacetimes, because in such a case, we will be able to obtain the counterpart of the Schwarzschild solution and the Reisner-Nostrum solution in these geometries. So let us go to spherical symmetric spacetimes. This is a particularly suitable spacetime for Ricci basic gravities, because in such a case, these equations can be solved. There is a technical aspect here. It's not that involved. It has to be with the metric that appears on the right-hand side, that in general appears the G, while you have the Einstein tensor of the Q on the left. So you need to put everything together upon the same metric. But you can always rewrite this in terms of the metric G if you have enough symmetry in your spacetime, which is in particular the case of spherical symmetric spacetimes. And then you can solve the equations. I'm skipping all the technical details because we have tried this thing with many different theories of gravity, with many different sources. And at the end of the day, for any RBG, if the energy momentum tensor have this kind of symmetry, where this kappa or k of rho is a certain function that characterizes your matter fields, then the line element, the spherical symmetric line element, can be always cast this way. Very simple, very compact, and there are just deviations with respect to general relativity solutions in these new objects that have appeared here, this omega 1, omega 2. And then there is something a little bit strange here. Instead of having r squared, we have r squared of x, of a new coordinate. But you can always express this in terms of this. Actually, this radial function that appears here is related to the radial coordinate here via also this function here. And the point here is that these two coordinates that appear here, the relation between them does not need to be monotonic. This is typically what you have in wormhole spacetimes, where the radial function is not a monotonic function. It has a minimum where it bounces off to another region of spacetime. Anyway, the physical radius is r squared, not x, because it measures the area of the two spheres. Okay? In order to look for the physical properties of your solutions, you need to focus on the behavior of r squared and not of x. It's just some kind of coordinate that we use that can go from minus infinity to plus infinity, while r squared has to be positive. Okay, so we have spherical symmetric spacetimes described by these two equations, where these functions a, gamma 1, gamma 2 depend on the theory of gravity and the matter fields we are using. It's not a problem. We can characterize many different solutions, and we are going to look for pathologies. You can check this paper if you are interested in details. I mean, you don't need to take notes because I will share this with Professor Alfonso after the talk, and then he will share it with you. Okay, so the first type of pathology we are looking for is something we are already familiar with, which is the idea of geodesic completeness. Okay, so we are going to see if this is spherically symmetric spacetimes, there are incomplete geodesics. We know that in general relativity there are incomplete geodesics, and then you can actually prove that this is the case for Schwarzschild and Reisner-Nostrum and Kerr-Newman solutions. We are going to see what happens here. So for any spherically symmetric spacetime of this form, which is very general, you can prove that the geodesic equation can always be written this way. This is not only for RBGs, for any theory of gravity. Actually, not making any reference to the theory of gravity here. Here, lambda is the fine parameter, which is the proper time for a physical observer. So E and L are the energy and angular momentum per unit mass, and K equal to 0 describes null geodesics, that's it, photons, while K equal to -1 describes time-like observers, that's it, physical observers. Now, if you plug this line element here, you get this expression. And this expression is nothing strange. Is for those of you who have already taken courses on classical mechanics, you immediately will see this is just the equation of a one-dimensional particle moving in an effective potential of this form. Okay, because you can always reabsorb this function omega 1 squared upon inside here, just introducing a new radial coordinate. Okay, so you can study this geodesic equation for all values of K and all values of E and L. And let us see if there is any incomplete geodesics. Null radial geodesics, that's it, photons with vanishing angular momentum, are particularly informative for this problem because they ignore this effective potential, because this L is equal to 0, K is equal to 0, so the effective potential is 0, and the geodesic equation can be integrated this way, very simple. Now, if you do this exercise in general relativity where omega 1 is 1, it's a constant, then this equation is immediately integrated, it gives you x, and then you have incomplete geodesics in this equation, because this x in the Schwarzschild solution will correspond when this omega 2 is also 1, so this r and x have the same meaning, and because r has to be strictly positive, when you integrate this, you will have x here, and then when x goes to 0, then there is no possibility of further extension of your space-time, because in that such a case, x is identified as the area of the two spheres in the line element. This must be strictly positive, and because of this, there is no possibility of further extension beyond the center of the Schwarzschild or the Nernst black holes. Hence, you have a geodesic incomplete geodesic. Hence, your space-time is singular. But this is not need to be so in RBGs. And actually, there are two different scenarios for this thing to restore geodesic completeness in RBGs. The first one, the problematic region, which is in the Dresden-Nostrom geometry, is r equal to 0, is displaced to infinite affine distance. These are the trajectories of geodesics coming in and out of the black hole. And as you can see, the affine parameter, which is plotted here, as we approach to some central region of the black hole, so we cannot go to r equal to 0. Actually, at some point, the geodesic just diverges. But this is no problem at all. It just means that the geodesic continues its path indefinitely. So they are complete. There is another scenario, which is this one. In this case, the geodesics can get to the center of the solution. This is what they do in general relativity. They get to the center, to here, to r equal to 0, but there is no possibility of further extension because it defines the radius, the area of the two spheres. This must be positive, so you cannot continue the solution to this region. But here there is no problem. The geodesics has some kind of deformation, crosses this region, and it can do it because the x is not limited to be greater than 0, r is limited to be greater than 0, but x does not. And because in these space-times, r and x have different meanings, so there is no problem in extending to the region x less than 0. And actually, you can prove that the radial function r is always greater than 0. Okay, so this is the summary that I'm making here. So here, it takes an infinite time to get to the center of the solution, or an infinite time to come out of the center of the solution, but these are geodesically complete. Here, you can get to the center and then cross to the region. Problem is that typically here at the center of the solution, when x goes to 0, the curvature will be divergent. So you will have curvature divergences. There are some exceptions to this rule, but in general, you have to face this problem. So let us face it, the problem with curvature divergences, because even if you have a geodesically complete solution, you could say, okay, but because curvature is divergent, for sure you will have some kind of physical pathology. And then I stress our physical intuition can be misleading. This is why I stress at the beginning of my talk that curvature is not directly observable. Only its effects upon physical observers is accessible. So tidal forces have a very intuitive physical meaning. So it's just that as you approach to some region with a strong gravitational field, your feet feel a stronger attraction than your head. So then you are spaghetticized like this way. And then at the end, because the curvature grows without bound, so then you are destroyed. Because the force here, the differential of force between your feet and your head is infinite. Does not need to be true. And to prove this, you can model a physical observer has some extension as a collection of geodesics, a collection of particles falling upon geodesics, which is technically known as a congruence. And what happens in a congruence is because there are tidal forces that affect each geodesic in a different way. So in general, these trajectories of the individual particles making your body will tend to separate or converge to the same point. You can study this problem from a technical point of view, just defining Jacobi vectors and then defining a basis, and from this basis defining a volume invariant that does not depend on the basis. And if at some point this volume element that defines the volume of a physical observer goes to 0, then you have a singularity that crosses 0 and utterly destroys 0. In the Schwarzschild case, what happens actually is that there is an infinite stretching in the radial direction and infinite contraction in the angular directions. This is why this popular word of spaghettization occurs. So this effect is what you have in Schwarzschild solution. And at the end of the day, your volume goes to 0, and then you are contracted upon a point, and then you are destroyed. When you do the same with these geometries, you do the same exercise, you find something weird, which is that the volume does not go to 0, goes to infinity. And there is not a proper interpretation for this. When you do this, so this approach is not useful for us, and then we find a way around of the results using something even more physical, because this is a bit, okay, we can intuitively understand what a volume invariant is, but I would like to have something even more physical, more direct, which is the following. Suppose that I have a congruence, different geodesics. They have the tidal forces that are modifying the directions. Okay, so I get from one part of the body, I start sending light rays from one part of the body to another, and on the round trip. So it goes from one part of the body to the other, and then comes back. And I measure the time of flight, how long it takes to travel upon two parts of the body. It is causal, because if the travel is not causal, in order for two parts of the body to remain together, you need a velocity above the speed of light, then the cohesion among the different parts of the body will be lost, and you will be destroyed. But if the travel is causal, then this does not need to be so. And then this is a bit, it's quite technical, actually. That's why I'm not writing any details. But you can prove that in these geometries, or at least in some subset of it, the causal contact between any two parts of the body is never lost. So this means that you have a physical body sustained by chemical interactions, like our bodies. And obviously, for these interactions to take place, the first condition you need to impose that these interactions are causal. And then it's just if they are causal, it's just a matter of how hard your body is to resist tidal forces. And this is actually what we find. That the physical interactions that is sustaining a body might be transmitted in a causal way. So tidal forces, defined by the divergence of curvature scalars, does not necessarily means that a physical body is destroyed. Okay, third kind of pathology we can look for. Because geodesics are a idealization of the parts of your body, actually, there are no point-light particles traveling in geodesics in the nature. All matter field is fundamentally a quantum field. It has some extension. So, idealized point-light particles traveling in geodesics is perhaps not the best way to deal with this problem. You should take into account the extended nature, quantum nature of a body. Because this is a very difficult problem to tackle, and there is no solution to this, as we usually do in physics, so we start doing approximations. Instead of dealing with the description of quantum electrodynamics about how nature should be, let us use another field, a scalar field, a free real scalar field, that is one. Separated as usual in modes, and study this propagation equation of your scalar field upon this spherical symmetric spacetime geometries, and in particular around the region where curvature can go to infinity. Then you get a wave equation, and with the wave equation, that is a standard textbook problem, you can compute transmission and reflection coefficient. As you can see here in this plot, with the transmission coefficient and reflection coefficient, that's it. The part of the wave that crosses through the center and the part of the wave that is reflected, so there is part of the wave that is dissipated, but you can always transmit and reflect, and there is no problem about this. The transmission and emission coefficients can be computed. There is no evidence of pathologies in the propagation of a scalar field upon the region where a curvature diverges. Okay, 4 criteria of pathologies. The theories on singularities make use of geodesic observers. That's it, geodesics in free fall. by the principle of general covariance, observers with arbitrary motions, that's it, observers with any acceleration, they should also have complete paths, because it will be very weird that you have a space-time where all the trajectories of free-falling observers are complete, but then as soon as you have a rocket ship, depending on the state of your engines, you can meet an incomplete geodesic. That will make no sense. This is why I'm stressing that general relativity, there is no discrimination is allowed between different observers. They all have exactly the same right to live. So, in addition to guarantee your space-time is geodesically complete, you must also guarantee that there is no observers with any kind of acceleration, as long as it's finite, to be physical, that have incomplete paths. When you study this problem, for any general spherical symmetric space-time, the geodesic equation, that will be this equal to 0, is generalized to this thing. And you get new contributions here. And this K of lambda describes the relative state of acceleration or deceleration of your rocket ship. And then you can study your favorite space-time with this equation to see whether this equation gives you complete trajectories, or in all cases, or not. When you do this, for instance, for this RBG theory, this quadratic theory, so then you can write these equations. Well, there are some technical definitions over here, but you can check that these motions, no matter what is the relative state of acceleration or deceleration in your space-time, they will be always finite. This equation will always give you a trajectory of your accelerated observer that can be indefinitely extended. So not only geodesic observers are complete in these geometries, but any other observer, no matter their relative state of motion, no matter what kind of forces he is subjected to, they will also be complete. Now, just to stress, I'm almost over, just to stress the breakdown of the correlation between the concept of geodesic incompleteness and the concept of divergence of curvature scalars, I'm plotting here this table from this paper, where I'm using quite a simple model, a quadratic f4 model with more or less simple energy momentum tensor like this form. And depending on the combination of these two parameters, sigma and beta, you are going to have 4 families of solutions, which I'm calling here case 1, 2, 3, and 4. And then I'm discussing here where there is wormholes in this space-time, what the metric components do, what the energy density does, what curvature scalars do, what geodesics do. As you can see here, they do not meet each other. You can have divergent curvature scalars, and the geodesics can be complete or incomplete, depending. Even there is a situation which is a bit even more weird, which is that the curvature can be finite and the geodesics are incomplete. So clearly, the divergence of the curvature scalars cannot be the reason for the incompleteness of geodesics. You have all kinds of scenarios. So these two things, curvature scalars and geodesics, are completely uncorrelated. And this is an important lesson to take from this kind of studies, that nature is not that easy as we thought it to be, in the sense that these two concepts are not related to each other. And the intuitive idea that we have about the curvature can be misleading, does not necessarily lead to pathologies. Pathologies in curvature scalars are not necessarily pathologies in geodesics, and the other way around. Okay, so this is my last slide, just to conclude. So space-time singularities, even 50 years after the development of the singularity theories, still define our understanding and physical intuition. We have learned quite a bit about what they are, but it will be also fair to say that actually nobody knows what a singularity is. And this is a problem, because we are used to upset this kind of arguments that in order to modify general relativity, we need to extend general relativity in the strong field regime, in the ultraviolet limit. And that when we do this, the problem with singularities, when we get to a better theory of gravity, the problem with singularities will simply go away. As you are seeing here, singularities are not understood yet. So when you say singularities will go away without knowing what singularities are, So can be very dangerous. So what I have done here in this talk is just build my favorite space-time and start throwing different criteria. I mean, attack my solution from different fronts with different machine guns to see what happens. So the first thing that I attacked it with was geodesy completeness. I just saw that there is no problem. Geodesy completeness can be restored via two different mechanisms. Okay, but there are curvature variances in your solutions. So surely this means that you have a pathology. Not the case, not necessarily at least. The intuitive idea that we have about infinite tidal forces ripping apart on physical observers, that is not necessarily true. Depending on your space-time, your observers could survive. Okay, let us agree point-light particles, which is an idealization of nature, to capture, even with a toy model, the fundamental extended behavior of matter. No problem, my model survives. Okay, but this is because you are using a very privileged kind of observer, those on geodesic motion. But there are other infinite other observers that travel in infinite varieties of acceleration and deceleration. What happens with them? Do they have the right to live? They do, and they actually do. They find the same complete space-time, and they can do they can mind their own businesses without nobody interfering on them. Okay, so this space-time survives these four criteria. It doesn't mean that there are no pathologies. There could be a fifth or sixth or seventh criteria here that you attack your solutions with that, and then you find that there is some pathologies, but not with these four, at least for these things. So the only thing that we can do here is to keep looking for further types of pathologies in specific spacetimes, and if these spacetimes survive your theory, the work upon different pathologies, so you can use these solutions to see if they give you also some interesting phenomenology for the problems that we have nowadays in general relativity, both regarding compact objects and black holes, and also in cosmology. And there are plenty. I am not mentioning any of these, maybe another seminar for the future, in case you could be interested on that. We'll also give a talk about that. And the bottom line of my talk is that the metric-affine theories of gravity, which is perhaps not as much studied as other approaches, such as quantum gravity, string theory, these kind of things. So, but they have a connection with real laboratory physics, with solid-state physics. They have a set of nice properties regarding the behavior, the second-order equations, they go free, and then you can see that you have just seen that there are singularity-free solutions in these theories, and there are also good news regarding the phenomenology in astrophysics. But this is a topic for another talk. So I stop here. So this is my talk by now. Maybe there is no, unfortunately, as a postdoc in UAPSO, I miss a lot the beach. There is no beach in Madrid, but there are other interesting things. So if you ever come by Madrid, please consider giving a seminar in my institution. I will be very happy to host you. Okay, so that's all. Thank you very much for your attention.
Okay, Diego. Thank you very much for your very nice talk, very interesting points. Eu vou falar em português agora para facilitar um pouco com o pessoal. Não sei se são muitos alunos ou como está a nossa plateia. Então, pessoal, quem tiver perguntas pode fazer em português, diretamente relacionadas a esse ponto, ou mais gerais, em relação a buracos negros, ou o que tiverem interesse em perguntar, por favor. Façam suas perguntas. Pode ser por voz ou pode ser no chat. Enquanto isso, eu queria fazer alguma pergunta para o Diego. Principalmente para aclarar, essa discussão é toda clássica, né? Uma discussão da descrição clássica do espaço-tempo, né? Dessas soluções, buracos negros. Então, você pode dizer, em certa forma, que pode... O pessoal fala que quanticamente a questão da singularidade seria resolvida, né? É como que o problema das singularidades é jogado embaixo do tapete, dizendo que eventualmente com a descrição quântica esse problema vai desaparecer. Você poderia comentar alguma coisa sobre isso? Se for em inglês ou português, como quiser.
Eu percebi. O inglês para mim, para questões técnicas é melhor.
Ok.
Então, so there are two things here. One I was mentioning already, which is that we tend to think that in order to solve the problem with singularities, we need to go to the quantum regime of the gravitational interaction. And there, I have two criticisms against that. The first one is that, so these quantum collections, as far as we know, so arise when your theory approaches the Planck scale. This makes sense because general relativity, as any other theory in nature, is an effective theory. It must come out from another more fundamental theory. Because we have this incompatibility between quantum mechanics and classical gravity, so we need to find some way or another to merge them into a single theory. Okay, so in order to do this thing, so we make our numbers with our physical constants. So we put there the physical constants that describe of fundamental theories, the speed of light, the Planck's constant, the Newton's constant, and then we make combinations to get new scales, and then we get the Planck scale. Now, the problems with that. The first is that the Planck scale, but from a fundamental point of view, is probably unlikely to ever be observed unless there are any mechanism that takes down to a much more accessible scale. The biggest problem to me is that if you are inside a black hole, when you get to the center, way before you get to curvature scales where comparable to Planck scale, purely quantum effects upon the matter field should occur. I'm not talking about gravity here. There are several kinds of effects that are very well known from quantum electrodynamics and from the quantization of fields in Fourier space-time that has nothing to do with Planck scale. It must appear way before the Planck scale collections appear. So my problem with that is that if you use a fully quantum gravity theory without taking into account the quantum matter effects, so to me it's clear that it's something that is not quite the case, because these quantum effects upon the matter field should occur way before the gravity effects. So a way out of this problem is instead of going for the big pot of the quantum gravity theory, use what you called, I usually use modified theories of gravity. Use it, use a different word, which is, can be extended theories of gravity. Here the approach is different. The idea is to use the approach of effective field theories, which tells you that no matter what is the fundamental theory of gravity, the effective field theory approach tells you, instead of using new objects, use the classical objects that you have in your classical theory of gravity, so metric, connection, curvature, and so on, and build an effective theory just by adding powers of the fundamental objects of your theory to build new actions. So for instance, you have the curvature scalar, and then you add the curvature scalar squared, and by dimensional consistent, you need to put some length scale in front of it, which is just the Planck's length squared. In that case, you don't need to know what is the fundamental theory of gravity. You are just capturing the effective dynamics of that theory, whatever that theory is, that you don't know, via an effective theory. This is something that is very commonly done in quantum electrodynamics and quantum chromodynamics. In such a case, then, because the Planck gravity collections will be strongly suppressed, so these effects will be tiny. And then you can study quantum gravity effects on effective scale and try to see how these effects will manifest at much lower scales than the Planck scale. And then also you can try to combine it with modifications to the matter fields via quantum collections. You can combine two things at the same time or forget about the quantum matter collections. And the second point is that, as I was mentioning, the problem is that you think that the quantum theory gravity will solve the problem with singularity. But I have just exposed it. What is a singularity?
Yes,
Because
of course. The problem is that the concept, the very concept of singularity, is not completely understood in a classical level. So that may be why people say that yes, okay, maybe quantum gravity will solve that, and then don't worry about that. Just put a firewall or just confide that you will have always a horizon that will protect you for whatever happens inside there. But right now that we are seeing mergers of black holes or objects that look like a black hole, what happened? A question that cannot be avoided is that what happened to the singularities in the binary? You have two singularities. You have two black holes. What happens with the dynamic of that point that will eventually merge into a one big black hole? And then what happens with the singularities? They go together, they find, and then they turn into a new point-like singularity, or they become a two-dimensional singularity. It's very strange that there is something that seems to happen there, and no one knows.
That's actually a very good question, because actually I was pondering about this thing, because we usually don't want to worry about space-time singularities because they are hidden behind a given horizon. And this needs to be consistent, because when you do models of gravitational collapse from a star to produce a black hole, some general relativity typically, but there are some exceptions, they give you solutions that are covered by a horizon, or solutions that even if they are not covered, they last for so long that there is no time to get to see the singularity. Problem is, if you have a merger and you simulate a merger of two black holes, what is the guarantee that when you do the merger, the final object that you get is not a black hole, a naked singularity? Because we use numerical simulation where we put our inputs, but we don't have a clear results that tells you that this scenario is not possible. Yes. Okay, so there are actually some studies about this thing dealing with the fact that what will be the signal if your merger of two black holes are either the progenitors are not black holes or the final object are not black holes. And there are differences as compared to the model of two black holes merging into a black hole. And actually there is experiments like from LIGO to LISA that are looking precisely for signals which will be characteristic of the fact that they are not black holes, right? Or some of the mergers are not black holes. They are looking for that. Okay, so the problem with that is that there is, okay, the Kerr solution is unique. There is Kerr and that's it. But models of objects or compact objects that are not black holes, there are plenty, there are many. And each of them has their own phenomenology. So you have to look for a different list of possibilities to check that it doesn't fit better into the data that you are observing that the simple model of two black holes, right?
Yes. And another thing, I don't know if there are any questions already. Please, people, if you have any question. So just complete that idea. Also, the fact that the accelerated observer, the incompleteness of geodesics are not related to their dynamics, as you showed. That I think that may have some manifestation in the process of the merging of the two objects, because if we imagine the black holes like balls, at some instance, at some moments where the horizon get in touch, the dynamics of the singularities are going to be important in the sense that they are already circulating. the objects are still in this world. So you won't have a singularity in the center from which you can measure the acceleration of other objects, the way the geodesics in that dynamical part of the process. The dynamics get really complicated, and then there is no anymore the central singularity. There are two singularities somehow. So what would happen to an observer? What would happen to the physics outside that?
Yeah, actually, it belongs to a wider question, because the structure of the curve solution has 4 horizons inside. So when you make into a dynamical situation, what are the horizons doing inside the black hole? And when they merge, how do they exactly merge to 4? This 4 and 4 makes to do other 4, how exactly?
And that has nothing to do with the quantum regime, because we are still in the very macroscopic and low curvature regions. So yeah, so that's what is very, very, very important and very interesting, that this line of research that you're developing. I would like to thank you. If there are no more questions, I would like you to please open your microphones and clap your hands for the speaker. I don't know if that is possible here, but okay. So I would like to thank you. Okay.
Okay. So thank you very much to the audience that attended to this talk. So I hope that you have been useful for you at any level. Anyway, so you have there Professor Afonso, which is, he's very proactive to talk about physics and possibilities for you. And that's it. Nothing else from my side.
Okay. Hope to see you again soon, and stay safe. Okay.
I will try.
I have an race already late in Madrid now.
Okay. Thank you very much.
Thank you very much.
Okay. See you.